for the next, I will be praising the skid resistance. So my name will be Muhammad Al-Shani Mahiri. So why the skid resistant method? The skid resistant method because the ability of the pavement surface to provide its friction and resist the uncontrolled tire sliding. The higher friction will support braking, cornering, and steer control, and also the water can form a lubricating film and reduce the tire surface contact. As we can see here, there is a road safety chains. Surface microstructure into the tire road friction and into to the vehicle control. And also, rainfall may reduce the friction and increase the skidding risk. So for the objective and the test variable will be test on the two types of surface, rough and medium pavement. The test condition, it will be 2 also dry and a wet condition, and the repetition will be 3 readings per condition, per test. So for the objective, to determine the average British pendulum tester for each condition, and to detect the quantity, to quantify the reduction in the skid resistance when the surface become wet. Also, the third one is the compare the result with the application with applicable JKR skid resistance benchmark, and the last one is recommend improvement and additional check for pavement safety. So this is the apparatus that we're gonna need. We're gonna need the British pendulum tester and all the procedure that will be conducted. So this is the safety and the quality control measure during our testing lab. But without further ado, let's jump into our video.
Power 7 or 6. Power 6. Power 7. One. My name is Musa bin Yusni, and today I will present about surface texture depth test using the sand patch method. This experiment was carried out under dry condition only, and the surfaces tested were medium surface and rough surface. This experiment aimed to determine the mean texture depth, also known as MTD, of a pavement surface. MTD is important because it shows the roughness of the pavement surface. It also indicates how well the surface can provide water escape path. In this test, only the dry condition was considered. The two surfaces tested were the medium surface and the rough surface. The volume of sand used was 50 ml. The equipment used in this experiment was sand, a measuring cylinder, a flat spreading tools or rubber disc, a measuring ruler, a pavement surface sample, and a brush for cleaning. The equipment must be clean and dry before testing to avoid errors in the sand volume and diameter readings. For procedure, first, the pavement surface was cleaned before testing. Next, 15 ml of sand was measured using a measuring cylinder. Then, the sand were poured on the dry pavement surface. After that, the sand was sprayed evenly in a circular motion using a flat spreading tool until it filled the surface board. The diameter of the circular sand patch was then measured using a ruler. Finally, the mean texture depth was calculated. For safety measure, during the experiment, several safety measures was followed. The test area was kept clean and dry. Care was taken to avoid sand contact with the ice. The rulers and spraying tools were handled carefully. The pavement sample was also placed on a stable surface. Any spill was cleaned immediately to prevent slipping. All students followed the laboratory instruction throughout the experiment. The formula used for the sand patch method is H equals to M4V divided by pi d square. For the medium surface, 4 diameter readings were recorded. The reading were 90 cm, 20 cm, 19.5 cm, and 20 cm. The average was 19.625 cm, which is equal to 196.25 mm. Using the formula, the MTD for the medium surface was calculated, which is 1.653 mm. This shows that the medium surface has a lower texture depth compared to the rough surface. For the rough surface, the diameter readings was 16.5 cm, 17.5 cm, 16.8 cm, and 70 cm. The average diameter was 16.195 cm, which is equals to 169.5 mm. The MTD was 2.216 mm. The rough surface produced a smaller sand patch diameter, which means the sand fill deeper surface void. Therefore, the rough surface has a higher texture depth. For the result, the medium surface recorded an MTD value of 1.653 mm, meanwhile the rough surface recorded a higher MTD value, which is 2.216 mm. This shows that the rough surface has deeper texture and more surface void spaces compared to the medium surface. Therefore, the rough surface provides better water escape path and has better drainage potential. In conclusion, the sand patch method was successful used to determine the MTD under dry condition.
Assalamualaikum and good day. My name is Nurul Amin Jannah Nur Azmi, and now I will be presenting our surface drainage test conducted as part of the highway engineering project.
Surface drainage is an important aspect of pavement performance because it ensures that rainwater is removed efficiently from the road surface. Effective drainage helps reduce water bonding, improves skid resistance, minimizes the risk of hydroplaning, and enhances overall road safety. So the objectives of this test are to evaluate the drainage performance of different pavement surfaces, to determine the time taken for water to drain from the pavement surface, to compare the drainage performance between rough and medium pavement surfaces, and to assess the importance of efficient surface drainage in maintaining road safety. The equipment used in this test includes a surface drainage test apparatus with a graduated transparent tube, a water container for filling the apparatus, and a stopwatch to measure the drainage time. During the experiment, safety precautions were followed at all times. We ensured that the test area was free from moving vehicles and pedestrians, wore appropriate footwear to prevent slipping, and handled the apparatus carefully throughout the testing process. So as for the procedure, first the pavement surface to be tested was selected, which included both rough and medium pavement surfaces. Next, the surface drainage test apparatus was placed securely on the pavement. The graduated tube was then filled with water up to the required level using the water container. Once the apparatus was ready, the water was released and the stopwatch was started simultaneously. The time taken for the water level to drain to the marked level was recorded. And to improve the reliability of the results, the test was repeated 3 times for each pavement surface. Finally, the average drainage time for each surface was calculated and compared. So the results obtained from the experiment are shown in the table. For the rough surface, the recorded drainage times were 5.12 seconds, 4.79 seconds, and 4.59 seconds, giving an average drainage times of 4.83 seconds. And for the medium surface, the recorded drainage times were 5.56 seconds, 4.77 seconds, and 4.20 seconds, resulting in an average drainage time of 4.84 seconds. The difference between the two average drainage times is only 0.01 second. So, based on the results, both pavement surfaces demonstrated very similar drainage performance. The rough surface drained slightly faster than the medium surface, but the difference of only 0.01 second is negligible. This indicates that both pavement surfaces are capable of draining water effectively under the test conditions. Small differences in the results may be due to slight variation in surface texture, the amount of water applied, or human reaction time when operating the stopwatch. Overall, the findings suggest that both pavement surfaces provide satisfactory drainage performance. Surface drainage is one of the key factors affecting pavement safety and performance. Efficient drainage prevents water from accumulating on the road surface, reducing the risk of hydroplaning and improving the friction between vehicle tires and the pavement. Good drainage also helps protect the pavement structure by preventing water infiltration, reducing pavement deterioration, lowering maintenance costs, and extending the service life of the road. So, in conclusion, the surface drainage test successfully evaluated the drainage performance of both rough and medium pavement surfaces. The rough surface recorded an average drainage time of 4.83 seconds, while the medium surface recorded an average of 4.84 seconds. Since the difference between the two surfaces is very small, both surfaces can be considered to have effective drainage performance under the testing conditions. This experiment demonstrates that the importance of proper surface drainage in improving road safety, maintaining pavement quality, and ensuring efficient highway performance. And that concludes my presentation on the surface drainage test. Thank you for your attention.
Assalamualaikum, my name is Shazafina binti Muhammad Asmadi, and I will be presenting the discussion, conclusion, and recommendation of this lab report. So the first that we're going to discuss is the analysis of surface texture depth. Based on the sand patch test result, the mean texture depth was calculated using the formula as shown. And what we got from the medium surface, the MTD is 1.653 mm, while for the rough surface is 2.216 mm. According to the JKR standard specification for roadworks, section 4, flexible pavement, the recommendation minimum baseline MTD threshold for Malaysian federal and state roads to maintain adequate high-speed friction is 0.50 mm. Typical dense graded asphalt concrete surfaces generally exhibit an MTD between 0.70 to 1.10 mm. And lastly, specialty premium mixes like stone mastic asphalt or porous asphalt often yield higher macro texture, ranging from 1.3 to 1.8. Both the median and rough MTD surfaces comfortably exceed the JKR minimum baseline of 0.50 mm. The rough surface high MTD indicates a highly open or coarse aggregate matrix, which is ideal for high stress zone or areas that requires enhanced friction. The second that we're going to discuss is the analysis of surface drainage tests. For the medium surface, drainage time is 4.84 seconds, while for the rough one is 4.83, which has 0.01 seconds in difference. Even though the rough surface has a significantly higher texture in depth, both surfaces clear the surface water film almost identical. This indicates that once a pavement reaches a certain microtexture threshold, well above 1.5 mm, the surface drainage capability for a given cross-fall slope is optimized. In Malaysia's tropical climate, where high-intensity rainfall is frequent, this rapid drainage behavior is critical to preventing hydroplaning and reducing hazardous splash and spray behind moving vehicles. The third is the correlation with skid resistance. For the rough surface, we have achieved a high dry mean of 118.3 BPN, which dropped to 85.3 BPN when wet. This represents a 27.9% reduction in skid resistance, retaining 72.1% of its dry friction. While for the medium surface, we have recorded a dry mean of 109.7 BPN, which dropped to 95.0 BPN when wet. This shows a lower 13.4% reduction, retaining an impressive 86.6% of its dry friction. For the JKR standards and safety compliance, less than 46 BPN is minimum for standard straight road sections, while for less than 55 BPN requires for high stress zones. So both the medium wet average and rough wet average are outstandingly high and well above the strict JKR safety threshold of 55 BPN. These surfaces provide excellent skid resistance and surely highly secure vehicle braking and maneuverability within the UiTM Shah Alam campus. In conclusion, the field study conducted at UiTM Shah Alam successfully fulfilled all three research objectives by evaluating the skid resistance, surface texture, and drainage characteristic of the selected pavement section in accordance to Malaysia engineering practice. For the first objective, the British Pendulum test demonstrated that both the medium and rough surface possess outstanding microtexture probabilities, yielding wet skid resistance values of 95.0 BPN and 85.3 BPN respectively. This value comfortably surpassed the strict JKR safety threshold of 46 BPN for standard roads and less than 55 BPN for high-stress zone, guaranteeing sufficient low-speed braking grip for campus traffic. Regarding the second objective, the sand patch test effectively quantified the pavement macrotexture, revealing the MTD of 2.216 mm for rough and 1.653 mm for medium. Both sections easily exceed the minimum JKR baseline requirement of 0.05 mm, confirming a robust aggregate matrix capable of disrupting surface water films. And finally, addressing the third objective, the outflow meter test indicates highly efficient and virtually identical surface drainage characteristic, with discharge time of 4.83 seconds for the rough surface and 4.84 seconds for the medium surface. In conclusion, both pavement designs are highly effective for the local tropical climate, providing superior drainage pathways and excellent wet weather friction that satisfy all JKR standards to ensure safe vehicle operations. Lastly is a recommendation. The first one for this is pavement maintenance and monitoring strategies. Biannual testing will ensure that proactive surface treatments such as microsurfacing can be scheduled before campus traffic compromises wet weather safety at junctions and pedestrian crossings. The second one is improving laboratory test precision and environmental controls. To improve, strict environmental control must be enforced, such as a windbreak ring should be utilized during the sand patch test to prevent fine sand grains from drifting and skewing the macrotexture calculation. And finally, enhancing drainage and safety assessment methods. Visual drainage tracking should be upgraded to digital logging or high-speed video recording to eliminate human reaction lag when timing the outflow meter. This ensures that the water cleared by the macrotexture effectively reaches the roadside drains instead of accumulating into localized ponds during intense monsoon downpours. That's all from us. Thank you for watching.